Okay, so just very quickly, the midterm. Okay. Midterm, Monday, October 9th at 6:30. The locations is going to be DH 1212 and DH 2210. So we have to split by names because there are a lot of students taking it online and here and stuff like that. So we just want to make sure that there is enough space for everyone. So the last names A to G is going to be in DH 1212. Last name H to Z is going to be 2210. Okay? This information is also going to be posted on Piazza. TAs will post it. The exam is going to be 75 minutes, 1 hour, 15 minutes. It's kind of duration of the class. 1 hour and 20 minutes, but it's going to be 1 hour plus 15 minutes. Closed book, no calculators, just bring your pen and ID. And, so you won't need anything for this exam. Okay? I mean, you can bring pencil and erasers and stuff like that if you want to, but ultimately it's just going to be, you're going to be provided with everything. Okay, let me just quickly go over everything that we've studied so far, everything that's in the lecture notes, everything that's in the reading material is a fair game. Let's see, everything up to convolutional networks and graphical models. So today we're going to finish graphical models, so everything is a fair game. Okay? Next class, we're going to start looking at restricted Boltzmann machines, specific classes of graphical models, generative models. That's not going to be on the exam. So the exam is going to include up to today's lecture. Okay? So what do you need to study? The first couple of, by the way, there's going to be probably 5 or 6 questions. Some questions are going to be fairly easy. Some questions will require thinking. Okay? My advice for everyone is try to write, try to answer all the questions. Because if you leave the question as a blank, you get nothing. Some professors are doing policies where if you write something and you write the wrong thing, you get negative points. I was thinking about that, but probably I'll give you more of a slack. So try to answer all the questions if you can. You will get partial marks if what you're writing is correct. Okay, so what you have to know, remember we've looked at the polynomial curve fitting, we looked at generalization, notion of overfitting. Remember we've looked at the loss functions, like squared loss functions, and remember when we looked at the decision, a little bit of decision theory, the fact that the minimum of this expected loss is the conditional expectation. You should be familiar with the definitions, how you derive these things, what is a generalization, what's the notion of overfitting. You have to be flexible with statistical decision theory, at least parts of it that we've covered. Then we've looked at a bunch of different distributions. So should you be familiar with Bernoulli, multinomial random variables, know what mean variances are, Gaussian distributions, both univariate and multivariate. What's the form, mean covariance, maximum likelihood estimation for these models, right? So this is all the basic stuff. You should be able to write, the likelihood function, be able to find the estimate those parameters. This is fairly basic. Remember your exponential family models when we've covered those. Sufficient statistics for exponential family models, and anything that related to that. Linear basis functions model, maximum likelihood, and least squares. This is the form of exponential family. And remember, when we write the likelihood, the log likelihood function, it's sort of, the maximum likelihood estimation for it takes this form, right, which is a basic least square estimation. So you should be familiar with those terms as well. You should remember, when we looked at the regularized least square, we've looked at regularization, right? This is a ridge regression. We've looked at the bias. We've looked at the bias variance decomposition, right? So be familiar with that. We've looked at examples where we have high variance but low bias, and the other way around, right? Low variance, high bias. So you should be familiar with that as well. Okay? Any questions? And everything we've covered is in the slides and in the reading material, Bishop's book and Deep Learning book. Okay, so for neural networks, you should be familiar with what is the feed-forward propagation. You should be familiar with types of hidden units, capacity of neural networks, how to train them, the loss functions. I'm not going to be asking you to derive backpropagation algorithm, but at the same time, some basic definitions of what the backprop is, you should be familiar with. You should also be familiar with dropout, batch normalization, and supervised pre-training, right? Everything that we've covered in class and what you've done in your homework. So I can ask you any questions about anything you see on this slide. Okay? So just be familiar what is a dropout, how you're applying, what's the batch norm, how you're applying, and so forth. Unsupervised pre-training, why do we need unsupervised pre-training, and such. Okay? And again, when you're using these deep networks to optimize, you're using squared error loss or cross entropy error loss, you should be familiar with those. Okay? Any questions? Yes? No, you won't need cheat sheet. Yes?
Will you give us the slide on the web?
Yeah, I'll put these on the web today. Yeah. In terms of the cheat sheet, there is nothing, I will not be asking you, if I ask you to write down the likelihood function for multivariate Gaussian, you should be able to do it. I'm not going to be asking you to write some complicated, mixture of student T distributions with definitions. No, that's, but basic probability, the thing that you should know about Bernoulli, multinomial, you should know Gaussians, these are friends. You should know squared error loss, you should know cross entropy error loss, and things of that sort, right? Okay, so convolutional neural networks, you should be familiar with local connectivity, parameter sharing, convolution, pooling, subsampling, local contrast normalization, rectification, stuff that we've covered in class. These are basic definitions of if I ask you something about convolution, you can actually get it there. And then graphical models. We've covered directed graphical models. We're going to cover undirected graphical models today. Just some basic definitions. For the graphical models, maybe there's going to be one question on it, maybe not. I haven't decided yet, but you should you should actually look at some basic definitions of chain graphs, linear Gaussian models, Markov blanket, conditional independence properties for both directed and undirected graphs, Markov random fields, discrete versus Gaussian Markov random fields, right? And MRS is something that we're going to cover today. Okay? Any questions? Okay, should be easy. It should be an easy exam. Should be a very easy exam. But you should be studying very hard, right? Because it's, 20% of your grade? So, okay. Okay, so last class we've looked at directed graphical models, right? We've looked at Bayesian networks, we've looked at belief networks, and anything that has to do causal, whatever you have a causal structure. So today we're going to look at undirected graphs, and in particular we're going to look at discrete graphs, and discrete graphs are useful for expressing causal relationships. So when we're looking at directed graphical models, right, we try to look at the causal relationship. There is always parent-child relationship. But undirected graphical models are useful for expressing, sometimes people call them soft constraints between random variables, right? And the idea is very simple. In many cases, if I look at the 2 pixels in the image, and I want to force some kind of constraints between those 2 pixels. It's not like I can say one pixel is causing another one. right? It really is basically saying, well, most of the time pixels within the same neighborhood should have the same value, right? Because if I take any image and I look at the pixels and I look at the surrounding pixels, they all kind of have the same value, right? They're not just random. The joint distribution defined by the graph is given by a product of non-negative potential functions over sometimes called maximum clicks or connected subset of nodes. And so the way that we define these distributions, P of x, is we say, well, it's a product of a bunch of these potential functions, non-negative potential functions, over clicks, right, over subset of the random variables, what kind of constraints we want to impose. And z here is known as the normalizing constant or partition function. And what you can see about this particular partition function, it's summing over all possible configurations of the states of x here. If it's discrete, it's the sum. If it's continuous, it's an integral. And typically for a lot of problems, with the exception of a few, this sum will be over exponential number of configurations, right? Over all possible configurations of, let's say, pixel intensities in your image. So these sums or these integrals are exponential. They're very high dimensional. And so we'll see some examples of using approximations to estimating these quantities, right? Markov chain Monte Carlo, variational inference, all of these methods are designed to figure out how we can compute these probability distributions, the log of the probability distributions, how can we approximate them. So for example, the joint distribution here over these sets of random variables, 4 random variables, is factorized as the product of these potentials, right? So there's AC, there is some constraint between AC, there's some constraint between CB, some constraint between BD, and so forth, right? So according to this graph, that's the probability distribution. And I have to specify what these potential functions are. They might have some parameters that I'm going to be learning and such. So let's look at the definition of the cliques. So the cliques, the subsets that are used to define potential functions that are represented by maximal cliques in the undirected graph. So for example, here you can see in this graph you have 5 cliques. You basically have pairwise cliques, right? x1, x2, x2, x3, and so forth, because there are edges between these nodes. And you also have 2 maximal cliques. And the maximal cliques are x1, x2, and x3, right? Because they're all connected to each other, right? And x2, x3, and x4, right? If we had an additional edge between x1 and x4, then the maximal clique would contain all 4 of these variables, right? But because this edge doesn't exist, then we don't have this maximal clique, okay? So if the potential functions that you're defining only involve 2 nodes in an undirected graph, the undirected graph has a very nice representation, right? Because it's just pairwise potentials. You can just write the product of just the pairwise potentials. If the potential functions involve more than 2 nodes, then there is a class of models called factor graph representations, just different representation. And for now, for the sake of this class, we're only going to be considering potential functions that define over 2 nodes. So maximum clique is going to be clique of size 2. But people who are looking at more advanced kind of models and incorporate more constraints, sometimes people think about high order potentials. You know, you can take 3 nodes or 5 nodes and construct some dependencies, some constraints between these different nodes, right? And again, these nodes could represent pixels in images, or these nodes could represent class labels. Typically, people use, you try to predict multiple classes at the same time, and you can incorporate these constraints by saying, well, if I'm predicting a person, then I'm more likely to predict another person, right? Or if I'm predicting a chair, I'm less likely to predict a car, right? Because chairs and cars, they typically don't, or like an office chair. If you're predicting an office chair and a car, maybe there should be kind of a negative link between these two, because if I'm detecting an office chair, it's unlikely that I should be detecting a car as well. But if I'm detecting a road, then it's more likely that I'm detecting a car, right? Things of that sort. So these random variables can represent pixel, but they can represent some higher level concept as well. So Markov random fields just defined as the product of these potentials each potential function is a mapping from joint configuration of random variables in a clique, right? So each random variable can take different values to non-negative real numbers. They have to be non-negative because probabilities have to be non-negative, right? Now, the choice of your potential function is not restricted to having specific probabilistic interpretation, right? Remember, in directed graphical models, we really do say it's a conditional probability of x given the parents. Here, these cliques, they don't necessarily have to carry any probabilistic meaning. They only enforce some form of constraints that you want to put on your graphical models. In many other cases, these potential functions are represented as exponentials, because sometimes it's easy to deal with exponentials. So what we can do is we can say, well, we can write this problem as exp to the negative of these sometimes called energy functions. And or I can write it as x to the negative of the energy function. And the energy functions and the relationship between energy functions and probabilities, this comes to us from statistical physics. So sometimes people talk about energies and its relationship to probabilities. Some people talk about potential functions and its relationship to probabilities. The two kind of, as you can see, are equivalent. In many cases, it might be easier. It might be easier to just specify the energy function, because the energy function doesn't have to be non-negative. It can be any real valued function, because when you exponentiate it, you have you only have positive. And this is sometimes known also as a Boltzmann distribution, right? You specify a whole bunch of constraints, you exponentiate, and you have a Boltzmann distribution. Now, a couple of and so when we look at later on, we look at Boltzmann machines. These are all classes of generative models, and they're sometimes called generative because we're actually specifying the distribution over your data. We're going to be defining that in this way, right? Specifying what the energy is and its relationship to the probability. Now, Markov random fields with hidden variables. So for many interesting problems, we're going to be introducing latent variables or hidden variables, right? So here is an example of a setting where your random variables contain both observed variables and hidden variables. So think of these observed variables as representing pixel intensity, so some data that you see, and you have these hidden variables, so latent variables. They're stochastic random variables. They can take different values, but they're hidden, right? So now your x is represented as v and h, the whole ensemble of random variables. You can specify the probability of your data, these visible variables here, as sum over all possible configurations of h, x to the negative in definition of some energy function, right? And we'll have to specify what that energy function is. For different problems, we might have different energy functions. And in general, in this case, computing partition function, first of all, right? In general, trying to compute this partition function, because this partition function is the summation of all h and v, right? It's a sum of all random variables, because you have to make sure for whatever configuration, the distribution has to be normalized. It's going to be intractable, except for special cases, right? And then parameter learning in these cases becomes a very challenging task. Right, because learning parameters in this model is fairly challenging. We'll see later why. Okay. Yes.
What is that?
Parameters. So you can think of these W's as specifying these are parameterized cliques, or parameterized pairwise potentials, or pairwise energies. Okay. We'll come back to this, I think, at the end of this class, just to get a glimpse of what they are. Conditional independence. So what these graphs tell us? Well, conditional independence is easier compared to directed models. In this case, observations block a node, which basically means that if there is, oh no, let me explain it while it's trying to recover. It's unlikely to recover, but so you're basically saying, well, if you have two sets of random variable, any path that's being blocked by C in this case, basically means that all of these random variables are independent of all these other random variables, right? And you can really derive it by just looking at the definition of the probability and really computing what the thing is. So it's easier, it's a little bit more intuitive. If there is no direct path from node A to node B, or any path is blocked by nodes in C, then they are conditionally independent. Right? Condition on C, A and B, variables in A are independent from variables in B. So let me do the no. Let me just make sure that the video stream is still working. Is that right? The video is still okay? Okay, good. Okay. So, so in this case, yeah, the two sets of nodes are conditionally independent if the observation block all paths between them. Okay? Which is if I go back to this particular model, which also has a very interesting property, because if I give you the states of H1, hidden variables in layer 1, then these V's are going to be independent of H's, which makes the inference algorithm a little bit easier to deal with, right? Because condition on one layer, the layer above and the layer below, they become independent, right? Which facilitates sampling-based algorithms that we're going to look at later. Okay, so the Markov blanket of a node is just simply all the directly connected nodes, right? So all the neighbors is the Markov blanket. It's much simpler than in directed models. There is no explaining away in these models. And the conditional distribution, conditional on all the variables in the graph, is dependent only on the variables in the Markov blanket, right? So if I want to do some kind of inference algorithm and I want to say what's the probability of this node given my neighbors, it's going to be independent of all the nodes in the rest of the graph, which is also a nice property for these models. Now, let's look at the conditional independence and factorization properties. Let's look at the two sets of distributions. The first is a set of distribution consistent with the conditional independence relationship defined by the undirected graph, right? So if I show you the undirected graph, and I look at all the conditional independence properties defined by the undirected graph, as well as the set of distribution consistent with the factorization defined by potential functions on multiple clicks on the graph, then these two distributions are the same. Okay? So if I specify it as a product of a bunch of potential functions, and I look at conditional independence properties, of course, these potential functions defined on the graphs with maximal clicks. And if I look at distributions consistent with the conditional independence relations defined by undirected graph, like via the Markov blanket, then these two distributions are the same. This is known as a Henle-Clifford theorem. So it basically means that this graph and this factorization property for this graph that respects these conditional independence properties, they're the same. So let's look at interpreting what these potential functions do, right, or these energy terms do. The potential functions, again, do not carry any specific probabilistic interpretation, right? So in principle, it gives, you have some more flexibility in choosing potential functions, right? And you can view these potential functions here as expressing configurations of the local variables. Which configuration of the local variables are preferred to others? So for example, you can say, you can incorporate the constraint by saying nearby pixels in the image should have the same value, right? So most of the time, that's the constraint. Obviously, sometimes this constraint will be violated because if you have an edge, then all of a sudden the intensity of the pixel changes, right? So there's some constraints that are going to be violated. And global configuration of all of these random variables with relatively high probabilities are going to be those that basically find a good balance in terms of satisfying these local constraints. And then these are going to be possibly conflicting, right? Conflicting constraints. Because if all the constraints are satisfied, then there's nothing interesting. Yes?
Potential function be optimized as part of the loss function?
Yeah, so in many cases, sometimes people define these potential functions by hand and say, I want to put this constraint, right? Because all you're doing is you're forcing local constraints on some local variables. And you're trying to find this global configuration. And obviously, there's going to be a few conflicting constraints, right? Like such an edge in the image, obviously, they will not have the same value, even though these constraints will say, well, most of the time they should. So the question is, how to find global configuration with high probability that satisfies a lot of these local constraints. But in many cases, these potential functions will have parameters that we're going to be fitting based on the data. And that's where the learning will come in. Okay? And so far, we haven't really specified what these random variables are. They're discrete, they're continuous, and for both of them, you can use the same type of inference algorithms. So let's look at discrete Markov random fields. And these are quite widely used in a lot of different applications. So MRF with binary variables are sometimes called Ising models in statistical mechanics and Boltzmann machines in statistical physics, but also in machine learning. These class of models, binary variables, how many of you have heard about Ising models? Okay, a few. These are some of kind of like very important class of models in statistical physics. They were developed, I actually don't know whether this story is true, but they were developed by Ising during his PhD thesis, right? So he introduced, these chains like Markov random fields with binary potentials in the 60s, I believe, in the 50s. And this is kind of became one of the most influential models. And Ising, I think he left the academia and was like a high school teacher somewhere else. It was a high school teacher, something like that. And his name is, very well known in the community because of these models that he developed, which is kind of interesting. So here we're going to be denoting the binary valued variables at node j as 0, 1. You can also do the same thing for 1, -1. And then according to the Ising model, the joint probability is going to be given by this expression. So let's look at this expression. We have probability of x. We have exponentiation. Now, if we wanted to actually, the energy function, we need the negative of this, right? So, but here we're just going to be looking at them as sum of ij for every single edge, xi, xj, theta ij, plus sometimes these are also called biases or external field in statistical mechanics, but here we're going to be calling them bias terms, right? So what does this particular potential tells us? If both of them are 1 and this theta ij is positive, then this is going to contribute to having a higher probability. Right? So you're basically saying, if two random variables are ones and the potential between them, or the theta, the parameter between them is positive, then that's good. Right? So that's just the definition. And the conditional distribution is, if I want to say, what's the conditional probability of this random variable taking value 1, conditioned on the rest of the random variable. Obviously here the Markov blanket is going to be for this particular random variable, the one in the middle here, it's going to be its neighbors, right? It's 4 neighbors, and it's going to be given by a logistic function. You can just derive it. It's very easy to derive it. So the parameter theta ij measures dependence of xi on hj conditioned on the other nodes, right? So it's exactly, if you look at this particular formulation, the logistic formulation, it's sum over all j's, or sum over all edges, or just the Markov blanket of theta ij, right? We're going to come to a specific example where you will see it a little bit clearer what's happening here. Oh yeah, it's here it is. Image denoising. So let's look at the example of noise removal in a binary image. Suppose you have observed noisy image. You're going to be describing it by an array of binary pixel values. Okay, so Y is your noisy image. It's a binary image. Think of like MNIST. MNIST is a binary image, right? Some pixels take value 1, other pixels take value -1 in this case, right? So Y here is your image. And then X is going to be noise-free image, right? And the way the generative process here is going to work is that we're going to take the real image, the noise-free image, X, and we're going to randomly flip the sign of the pixel with some small probability, right? So think of it, you have some ground truth image, and the way you corrupt it is you just flip every pixel with some probability, and then what you observe is you observe the corrupted image. Okay? And so now the question is, can you denoise, can you figure out what the states of these random variables are based on the noisy image? Okay? So we can specify the energy function. So let's look at what this energy function would do. The first term here, xi xj, is basically saying neighboring pixels are likely to have the same sign, right? Because if both of them are positive or both of them are negative, and then it's, it will have higher probability, right? So this particular pairwise is exactly what these pairwise potentials are saying. It's basically saying I want neighboring pixels to have the same sign. And then you have this additional term. This additional term is basically saying that noisy and clean pixels are likely to have the same sign, right? Because that's another constraint. You're basically saying most of the time they should have the same sign. Occasionally it's going to be violated, but they should have the same sign. And here you have a bias term, right? The bias term is kind of like measuring how much black versus white you should have in the image, right? And now you have these parameters, h, b, eta. These are parameters of the energy function, and depending on the choice of these different parameters, you can set them. If you set b to be high, then you're basically saying, no, I really want my neighboring pixels to have the same value. I'm quite confident about it. Or if your eta is high, you're basically saying, no, I really want to copy my noisy image to the real image. Yes?
So is this X just the noise-free version of Y?
X is noise-free version of Y. You're trying to decode it. You're trying to say, can I get the noise-free version? But obviously, you see there is a violation between the term that looks at the pairwise xi's and the term that's looking at xi yi, right? Because if the noisy image, if the pixel is flipped, and the ground truth, let's say the flipped pixel is -1, the ground truth is 1, then it's violation. So you kind of, for the denoising, you're kind of saying, well, I want my neighboring pixels to have the same value in the true image, but sometimes I have some noise, right? At the same time, it should be reflecting off the image, but again, because of the noise, sometimes these constraints are going to be violated. And so here's an example of how you can do image denoising, right? By fighting between these two different constraints. You can use something that's called iterated conditional modes, which is just coordinate-wise gradient descent. Right? In coordinate gradient descent, all it's doing is basically saying visit unobserved nodes, these x's sequentially, and set each x to whichever of its two values has the lowest energy or highest probability. Right? So you've given some instantiation of the x's. Maybe you can instantiate all the x's with y's initially. That's your initial point. And then you go for every single x, you look at its conditional probability, which is a logistic function, and you say, is the probability of being 1 higher than the probability of being -1? And you just set it to the highest probability. And you just iterate sequentially. So this only requires us to look at the Markov blanket, the connected nodes. And in this case, the Markov blanket is just simply all of the directly connected nodes, right? Because it's structured on a graph, 2D graph, it's just the neighbors. And so if you have a noisy image, you have a regional image, this is what you get by doing iterative conditional modes. Right? So it's not perfect, but it gets rid of some of the noise. Okay? It really is just basically saying, well, there's some inconsistency because my noisy image has -1, but all my neighbors in the true image has they have +1. So how much do I want to fight that? Right? Any questions about this? Very simple algorithm, but somewhat efficient. Yes?
So basically, this result just based on percent of each beta, and we have that two random.
Yeah, that's right. That's right. So hyperparameters in this model are h, beta, and eta. Right? And they're just 3 parameters that control how much control you want to have over, fighting between noisy image and the clean image versus the neighborhood defined in the clean image.
So smaller than the threshold, then
Yeah, typically you just set it 0.5. You look at the conditional probability. So if I just go back, maybe just to clarify. No. What's happening here? So let me go into another class of models, which are called Gaussian graphical models. And these are heavily studied models. If you look at the literature, they have certain nice properties. So let's say we have observations that have a multivariate Gaussian distribution with mean and covariance matrix, right? That's the definition of the multivariate Gaussian. Okay? Now, the Gaussian distribution represents, remember, the second order relationship, right? It's mean and covariance between two variables. It basically encodes a pairwise Markov random field, right? You're incorporating second order statistic. And so what I can do is I can write P of x in this way. I can say it's x transpose jx, right? And if you look at the matrix, it's just going to be xi, xj, some parameter jij, right? In this particular formulation. So J here is going to be the inverse of the covariance matrix, sometimes called precision matrix. And mu is going to be defined by, precision matrix time the vector G here, which just incorporates all the bias terms. So because your covariance matrix is positive definite, your J is also going to be positive definite, and it's sometimes known as a precision matrix or information matrix. And it's sparse with respect to a given graph, right? So if Ij, if there is no link between Ij, then the corresponding elements in the information matrix is 0. So in this case, Gaussian graphical model really is enforcing or sort of constraining it to be sparse information matrix, sparse precision matrix. Okay, so the absence of links really is telling me something about precision matrix. This is again known as a Gaussian graphical model. Right. And again, x transpose jx, I can write it as pairwise potentials plus unary potentials. Okay. So there is a lot of work where people are trying to figure out. I have seen some large-scale, high-dimensional data. I'm trying to infer the second order potentials. I'm trying to infer some precision matrix, and the sparsity that I incorporate in my graph will effectively incorporate sparsity in precision matrix. Remember, sparse precision matrix, the inverse, the covariance matrix could be full covariance matrix, right? But here, precision matrix could be sparse. You say saving on the number of parameters that you have to specify. So in this case, yeah, the information matrix is sparse, but the covariance matrix is not necessarily sparse. Any questions about this particular model? When people are using Gaussian graphical models, the whole bunch of work done in this space. How do you efficiently estimate it? Because it's one of the models. Whenever you're dealing with high-dimensional data, and you have some topological structure to how different maybe features in your data, dimensions in your data should be interacting, you can incorporate that into the graph. Yes.
If you wanted to deal with third-order factors here, I mean, you obviously could do with just this, but is there like a generalization or something? Yeah, there is like, we're going to talk about restrictibles machines, for example. There is something that's called third-order models, third-order Markov random fields, third-order Boltzmann machines, where you're actually looking at interactions between three variables. So these are much more, potentially more interesting models, but also much harder to fit and train and stuff like that, right? So, yeah, but there is a generalization for sure. Yes? So here, sometimes it's called third order, but really just basically you have three variables, and you're defining energy function over those three variables, right? Yes?
How do you write out that P of x from the normal distribution?
From what?
From the Gaussian distribution?
Oh, that's basically, you just look at this equation, and you kind of like fit it in here. Because it's just a simple linear algebra converting the Gaussian distribution to this P of x. Right? It's just a simple, because what you basically have terms that depend on x squared, and you have terms depending on x, and that's all.
So what I mean is that, so basically P is basically just another expression.
Yep. That's right. Okay, so let's look at one of the class of models called let's see, a class of models called restricted Boltzmann machines. So what we're going to do is that and we're going to cover this model in our next class. But for many kind of, when I mentioned, there's a lot of, whenever you're dealing with real world problems, you have to introduce hidden variables, so latent variables, right? In order to be able to learn some features or some data dependent structure, you have to have some latent variables. So what I can do is here I can say, well, I'm going to have random variables that are containing my visible variables, which is, again, think of them as pixels in the data. And you have hidden variables, which, again, binary Bernoulli random variables, binary random variables. And you have this interesting bipartite type of a structure. Right? There's only connection between hidden and visible, but there is no connections between hidden variables. So you have stochastic binary variables V, and you connect it to stochastic binary hidden variables H. Now, in this case, V is going to be 0, 1, and H is going to be 0, 1. And we can define the energy function this way, much like what we've seen in our previous example with the Gaussian MRF, right? Just looking at the pairwise. So you're looking at the ij. I is the set of all the visible variables, say pixels. J is the set of all the hidden variables. And I'm just looking at these interaction term Vi, Hj, right? Again, what is this telling you here? If Vi takes value 1 and Hj takes value 1 and Wij is positive, then it basically, it's more likely to have that configuration. It's more likely to contribute to positive probability. If Wij is negative, then it's basically saying I don't like this configuration. Okay? The probability of the joint configuration is again going to be given by the Boltzmann distribution. I can write it in terms of the negative of the energy, or I can write it as bunch of product of potential functions, whichever way I want to write it, right? Because they're the same thing. I can say, well, there's a whole bunch of potential functions. Each potential function is going to be Vi, Hj, Wij, depending on my parameters W, plus these unary potentials. Or I can write it as an energy function, right? Okay? Now, these models are called restricted because there is no interaction between hidden variables. Okay? And now if I look at the properties of the Markov blanket, it turns out that inferring the distribution over these hidden variables is quite easy. The reason why is because I can say, what is the conditional probability of H given V? Because what's the Markov blanket? Given V, if I give you the states of all the visible variables, the two hidden variables become independent, right? Because there is a path, you know, if I want to go from Hi to Hj, I have to go through V. And if I condition on V, they all become independent. And so here I can say the conditional probability is just going to be given by the product of these conditional probabilities. And you can prove it by just writing down expressions on how, you know, what the factorization is, and you can actually derive it. Just looking at the joint, looking at the conditional, and just doing a little bit of algebra. And so in this case, the conditional probability is given by, again, the logistic function. It's just an instance of an Ising model. Similarly, for P of H given V, we can basically say, well, this conditional is given by logistic function, right? And again, these are Markov instances of Markov random fields. Sometimes people call them Boltzmann machines. Sometimes people call them log linear models. And the reason why sometimes these are models called log linear models is if I go back to the definition, if I take the log of the joint, it's going to be linear in the parameters, right? So log linear is the log of the joint, it's linear in the parameters. The marginal distributions are not linear, but the joint is linear in the parameter. Okay, so Boltzmann machines, and again, we're going to get into details as how we're training, but I just wanted to highlight, you know, what can we learn here? Well, if we have observed data, then if we actually learn those parameters W and visualize them, they will look like this. right? Did you see something like this when you were training MNIST classifier? No? Close? But the idea here is, again, if you give me, again, it's a generative model, so give me a new image, the intuition really is that given the new image, I infer the states of the hidden variables. And if I want to do some kind of reconstruction of the image, then the reconstruction of the image is going to say, well, it's a bunch of these filters, you're adding them together, passing it through the sigmoid, and these numbers are given by the conditional probability of these hidden features being activated. Right? So if you think about, given the image, you activate the states of the hidden variables. These are probabilities. If you're trying to reconstruct, that's what it would look like. So again, it's kind of finding these features, and each node here. So this is just a representation of a particular hidden unit and its connection to the entire image, right? And so now you can represent this new image as kind of as a representation, it's conditional probability, right? Much like what you have in neural networks. Given the image, you do the first pass, which is a sigmoid. It's exactly what you're doing here, except for it's also a generative model. So you're actually trying to model the distribution over pixels. You can also define energies for different data modalities. So for example, if you're dealing with real valued data, you can specify the energy in this way. Right? And remember, I can always say probability of x is e to the negative of the energy. And there are multiple ways of defining energy for real valued data, but this is one of them. So again, you have squared term for vi, and then you have some interaction term between vi and sj, and some bias term for j. Right? And it turns out that in this case, you can actually show that the conditional is given by the Gaussian, and the conditional of h is just given by Bernoulli. And the Gaussian distribution, think about the Gaussian distribution, the mean of the Gaussian distribution is given by weighted average of the states of the hidden variables, right? So this is sum of all hidden variables that are going in the particular visible variable r, I weighted by wij multiplied by sigmoid. It's another parameter that you can learn or you can specify. Okay? So there has actually been a few papers that showed extension of these models to other members within exponential family. So if you're dealing with Poisson data, folks who are looking in neuroscience domain, they like Poisson distributions, modeling spike data, you can do that. If you're working with count data, like bag of words representation, you can define, again, distributions in a similar way. Right? So here is an example of Gaussian Bernoulli RBM, and if you train this model, and we're going to see how we're going to be training these models, but it recovers these edges. And if you actually use multinomials as your data, or multinomial distribution over the input space, which is suitable for modeling count data, you can discover these kinds of topics. Right? So the idea here is, again, if you think intuitively about each image, is made up by some combination of subset of these features. And each document here, or these are news stories, is made up by some linear combination of these learned topics. So there are these extensions where you can think of these models as undirected versions of topic models. Like if any of you are familiar with latent Dirichlet allocation or any other one of those topic models, this would be an undirected version of it. Now, relationship to directed graphs. And again, we're going to dive into the model, and we're going to start seeing how we can train these models, how do we do maximum likelihood estimation, all that good stuff, so that you have an intuition of how to deal with MRFs, Boltz machines, deep Boltz machines, and such. But relationship to directed graphs. Let's look at one. Let's try converting directed graph into an undirected graph. Okay, so why do we need both of them? So let's look at this chain graph at the top, right? x1, x2 up to xn. I can always write it down as a series of conditional probabilities, right? According to this graph, right? That's just a chain. That's just a Markov chain. So my future always depends, it is always independent on the past given my present, right? So that's why you just have these bunch of these conditionals. Now, if I look at this graph, it's also a Markov chain. right? I can specify it as such. I can just put the potential on every single one of these pairwise nodes. I can normalize it and have it that way. And it turns out there is one-to-one correspondence. I can always say in this case that my potential here, pairwise potential, is going to be defined as this probability, joint probability. My next potential is going to be defined as a conditional probability, right? I can always make this connection. In this case, the two are equivalent, right? So the question is, what's happening here? Well, it turns out that the directed graphs can be more precise about independencies than undirected graphs. Okay, let's look at this example. So what is this example saying? This example is saying the way my joint probability factorizes is I have priors over x1, x2, and x3. So there's p of x1, p of x2, p of x3, and then I have the conditional probability of x4 given the parents, right? So for example, remember when we looked at the image generation property, x1 could represent identity, x2 can represent position, x3 can represent orientation. I sample those and I generate my image, right? But the problem is that if I do the conversion to undirected graphs, this particular conditional probability involves 4 variables, right? So I would have to introduce a click in undirected graphs with these 4 variables. And if I do that, I can't really be precise about the nature of this conditional probability. So the way that you do the conversion from directed graphs to undirected graphs is you do the process called moralization. You marry the parents, right? So you marry the parents, and if you marry the parents, you basically have this graph. But this particular graph is, it can't really model these conditional independence properties, right? Because you have this 4th order click, and what is the 4th order click? The 4th order click is just anything. You have 4 variables, you have a 4th order click, you can model anything. There is no conditional independence properties. So you cannot really model the conditional independence properties defined by this graph by just doing that. So here all the parents of x4 can interact to determine the distribution of x4, right? So these things can be interacting to determine what this thing is. So the directed graph represents independencies that the undirected graph cannot model. And again, here to represent the high order interaction between these 4 variables, you have to create this 4th order click. And the fully connected graph says here did no conditional independence properties, right? So if your graph is fully connected, it can represent any distribution, right? So it's not as precise. It's just basically, if you give me a fully connected graph, you haven't really told me anything. Any distribution will satisfy, the fully connected graph. Yes?
Is there any correspondence between the concept of directed and undirected models and the concept of locally normalized versus globally normalized models?
So directed models are always normalized, just by definition, right? Because you can always say it's just a bunch of conditionals, and you have a valid probability distribution, right?
What about globally normalized models?
What do you mean by globally normalized?
The concept of locally normalized versus globally.
So for directed models, typically when you specify the joint, you have to specify the joint as a bunch of conditionals. So it has to be globally normalized. You don't need. That's why we don't have normalization constant. For undirected graphs, when we enforce the constraints, so sort of like local constraints, in order to make it globally normalized, we have to have a partition function, right? To have it be normalized. But on the other hand, undirected graphs can be more precise about independencies than directed graphs, right? So let's look at this particular graph. Okay, what is this graph telling me about conditional independence properties? This graph is saying that A is not independent of B. Okay, this graph is also saying that A is independent of B given C and D, right? It also is telling me C is independent of D given A and B, right? It turns out that there is no directed graph over 4 variables that represents the same set of conditional independence properties. Exact same set, right? You can construct a graph where it sort of like has this property but more, but you cannot really specify a directed graph over 4 variables that has these specific properties, right? So you can see that in some cases, depending on what you're trying to do, directed graphs are more suitable. In some cases, again, depending on what you're trying to do, undirected graphs could be more suitable, right? And so think of this Venn diagram, right? And think of the space of all possible distributions you can characterize. There is a subset that corresponds to directed graphs. There is a subset that corresponds to undirected graphs. There are certain distributions that can be modeled by either one, and there are certain distributions that can't, right? So for the Venn diagram, you have a set of all distributions P over the given set of random variables. You have a set of distribution D that can be represented as a perfect map using the directed graph, right? The perfect map that satisfies all the conditional dependence properties. And a set of distributions U that can be represented as a perfect map using undirected graphs, right? So that's kind of what we have. So in this case, I guess the distribution is reflected in the graph and vice versa, and the graph is a perfect map, right? So relationship between conditional dependence properties and what kind of graph we're specifying it with. Now, you can extend this framework to the graphs that include both directed and undirected models. And there are classes of these models called deep belief networks that are combining directed and undirected graphs, but you have to be very careful how you do it. There's been a few papers that were attempting to do it, but you have to be very careful. You can't just kind of like draw arbitrary graphs because that might not correspond to valid probability distribution. So you really have to be able to write down the joint distribution of all your random variables and make sure that's a valid probability distribution, particularly when you start combining one with respect to another. It can sort of be non-tractable or might not be a valid probability distribution. Okay, so for the rest of the class, not the rest of the class, the rest sort of chunk of the class, we're going to look at undirected graphs like restricted Bose machines, deep Bose machines. These are instances of deep Bose machines. These are instances of undirected graphs, and then we're going to transition to directed graphs, which are the instances of something that's called Helmholtz machines, as well as variational autoencoders, and generally, generative adversarial networks. You can think of them as directed graphs. You have some prior, and you specify conditional probabilities. So we're going to look at the advantages and disadvantages of both of them. Okay? Okay, good. So we're done for today, and again, you have enough to study for your midterm.